So good evening to everyone. My name is Varun and my topic for presentation was wireless EV charging and the inductive power transfer technology. So in this PPT I'm going to explain few things, that is the basic principle of how inductive power transfer works, that is understanding the electromagnetic induction and uh, how the charging actually happens. Then we move on to the recent advances, that is as of 2025 what are the new advances that have been developed in terms of efficiency, power levels, etc. Then we will go into the real world applications, that is where actually this charging is used, IPT charging is used. And finally we'll see the advantages and limitations and future outlook. So let's start with the basic fundamentals of how does wireless EV charging actually work. So the basic principle is that this charging operates through electromagnetic induction. That is, when you have AC current that flows through a transmitter coil. So this is the primary coil, which is basically going to be on the ground or on the charging pad. So when AC current flows through the primary coil, this creates a magnetic field, and this magnetic field induces a voltage or a current into the coil that is mounted on the vehicle. So that is a basic principle that you can see, that is the AC current flows through the transmitter coil which is on the ground. This creates a magnetic field, and this magnetic field induces a voltage in the coil that is mounted on the vehicle. So thus this contactless energy transfer thus eliminates any physical connector. So we don't need to have any kind of physical wire or connection. Just based on the magnetic fields itself, we get to see the charging. So you can see in the image also how like the on the ground you will have the large AC like AC converters, and this creates a magnetic field, and this magnetic field is then induces a current in the receiver, and then the car's mounted devices will convert it back to DC and charge the battery. So that is the basic flow. There's certain terms that we need to know for this, is that the magnetic coupling, that is both the coils, that is the primary and secondary coil, must resonate or must be tuned to the same frequency in order to ensure for maximum efficiency and power transfer. And then another factor is the resonant frequency, that is the quality factor and coupling coefficient should be like basically this frequency determines how efficient the charging happens. So now I'll explain how the charging works more depth. So the grid AC power, that is the power that is going into your the ground coils. This AC power is converted to high frequency AC using certain power electronics and inverters to enable efficient wireless transfer. Then this high frequency AC then energizes this transmitter coil, that is our ground coil, which is uses Litz wire, thus creating a magnetic field. Then, because of the creation of the magnetic field, the magnetic flux crosses the air gap between the ground pad and the receiver coil that is in the vehicle with a efficiency of 90 to 94%, that is by using the resonant coupling. Then the receiver coil in the vehicle then takes this AC voltage and converts it into DC, and gets an output of DC, 400 volt DC, and this is then used to charge the battery. So you can see here the battery charging also. This is a basic diagram that shows how the AC current flows to your electrical pads, and then it goes into your the receiver pad of the car. Now these are the 2025 technological breakthroughs. So first is the 11 kilowatt standard system. So commercial 11 kilowatt wireless chargers now achieve up to 95% efficiency with the improved coil designs and other alignment changes. Then dynamic charging roads. So there are multiple vehicle roads, especially for example the one in Detroit, where it enables charging while driving. So this is based on embedded coils, so coils that are present within the roads that provide a 19 kilowatt power transfer. Then you have AI powered optimization. So ML algorithms optimize this power transfer in real time, which compensate for certain environmental factors and alignment issues. Then we have enhanced safety systems. So advanced foreign object detection and live-in object protection systems meet good safety standards. So these are the real-world applications. So we know that wireless charging is very much common nowadays, especially in the public transit systems. So many EV buses, EV cars, even private cars, all are like converting into EV, and that's why this wireless charging has come to a massive role. So we have Induct EV, which is a company that has installed 200 plus wireless chargers for the buses, for the EV buses across US. Um, this reduces their fleet size by 15 to 20% through proper charging. Then in commercial and industries also, in BMW have like their offices have installed wireless charging options for all their equipments. Then Mercedes EQS with 11 kilowatt wireless charging, and even the warehouse uses certain chargers. Next we have certain residential solutions. So in the residence also they need to have for example to charge their private Teslas and EVs. So we have V-Tricity Halo, which basically gives you wireless charging for your Tesla, because Tesla actually has wired charging, but this provides wireless charging. And similarly they can integrate their garage floors with this EV charging to have really good efficiency and easy charging. Next we have the advantages and limitations. So the key advantages of using IPT and wireless charging is that it has unmatched convenience, because since it is just kept on the floor on the road or integrated or embedded on the road, you don't really have any maintenance, or it's very convenient to use. You just have to drive over it, or place your align properly over it, and it starts charging. Then weather resistant operation, doesn't matter what the weather is, as long as there is a good contact between the or proper alignment between the primary and secondary coil, it is going to work with good efficiency. Then reduce wear and tear, enhance safety, and because there are no exposed connectors. So for example in the wired charging, there are some cases where the connectors fail or they're faulty, but all of these are mitigated in the form of when you use wireless EV charging. The current limitations are obviously the higher installation costs. It is 2 to 3 times greater than using wired connectors, and there is a efficiency loss because there is no wired connection. Anything that happens wirelessly has some form of loss. So there is a transmission loss when the current tries to go from the primary to secondary coil. Then there are limited power levels. We cannot reach the efficiency or the throughput that is given by wired chargers. And certain standardization challenges, that is alignment issues. You have to get a general alignment for all cars or all uh, equipments, etc. Then certain technical barriers, you have EMI EMC compliance, the coil alignment precision, because the different vehicles or different devices will have different alignments for the coil, so that is one of the major issues. Then thermal management and interoperability between the manufacturers. The future opportunities are having dynamic charging infrastructure, which I'll explain in the next slide, autonomous vehicle integration, smart grid connectivity, etc. So this is a dynamic vehicle charging process. So here is this is kind of used already in certain roads in the US, where you have sensors that detect your vehicle presence and initiate the communication with the receiver coil that is present inside the car. Then after this connection is done, the power activation happens. So the embedded coils activate as the vehicle passes. So this is more like the wireless charging roads that are present. When you drive over it, your battery starts charging. How this works is because the coils activate in a sequence. So these primary coils are placed in sequences in the roads, and the moment the vehicle is detected in sequence, these coils start activating and provide continuous power transfer. Then we have real-time monitoring. So AI systems optimize this delivery based on the vehicle speed, battery level, traffic conditions, etc. This is a final future outlook and my conclusion. So by 2030, it is expected that the wireless EV charging will transition from small applications to mainstream adoption. So because we know that having wireless charging or having EVs is the future to reduce pollution and global warming and etc. Then the key developments include having 22 kilowatt plus systems, having universal standards, integration with smart city infrastructures. Then the convergence of 5G, AI, IoT, etc. will be able to will enable the predictive charging and vehicle to grid capabilities. So that is it from my side. Thank you.